All right, guys, welcome to week 3 of file system forensics. This week we're going to dig into our first actual file system. We're going to look at the FAT32 file system and some of the details regarding it. Now, as you know from the reading, there are a couple of different flavors of the FAT file system. There's FAT12, FAT16. These are earlier iterations of FAT. Prior to that, it was just called the DOS file system. This is back when files that needed to be saved were just flat data files, text files, CVS files, very small footprint, right? And so they didn't need a lot of file space. I mean, they didn't think they'd ever need a hard drive bigger than, 200 megabytes or something like that. So the FAT file system is for smaller files, and it's been adapted over the years up through Windows 95 to FAT32. And it's still in use today. Well, where is it used? It is used typically in smaller removable media like SD cards or small USB drives. They may be formatted for FAT32, and it's good. It's good for drives up to 2 terabytes, I think, is FAT32's limit. Here's what the disk architecture looks like. I'm going to move myself out of the way here. In fact, I may just move me completely off screen here at some point because I don't really need to be here. You don't need to see my face, I guess. But here's basically what happens when you format a disk with the FAT32 file system. It sections off a whole chunk in the beginning of the disk for administrative stuff, right? This is reserved stuff for the file system files, or they're not even actually files in the FAT file system. They're just data tables that reside on the disk, and we'll take a look and see what these things look at. But you might have some HPA or some DCO space at the beginning, or it may just be reserve space for like the master boot record. Okay, so we'll take a look at that. And then after the master boot record, you'll have your primary volume boot record, and then you'll have a few reserve sectors, and in this case I think there's actually 3 reserve sectors, and then you'll have a secondary volume boot record, and it's really just redundant. It's just a backup boot record for the volume. Now in this case we're not looking at bootable media, we are just looking at an SD card, a very small SD card, just for the sake of sharing this concept with you. So we have this, and then there's a whole bunch of reserve sectors. This is not to scale, this image here that we're looking at. There's not just 4 reserve sectors. There's a multitude of reserve sectors. And then they put the FAT tables. That's redundant. It would be the file allocation table. I guess we refer to them as FAT tables, but that's like saying file allocation tables. But anyway, that you'll have a table 1 and then table 2 also built in for redundancy. A key difference which may appear on tests, and you should know from FAT16 and FAT12, they were similar, and then there was a departure in the structuring of the disk architecture to FAT32, and that is, prior to FAT32, the root directory, in other words, the index of all of the files and folders in the root, was previously in this system space back here, and not out in the data space. Well, FAT32 moved the root directory out there to the data space, which allowed it to expand to fill the volume, which means you could store more files on the drive. Okay. So that's the basic architecture. We'll take a look at that and see what it looks like. Here's just a screenshot, and then we're going to move into actual my live FTK imager that I have running with the SD card. But basically, you're familiar seeing if you image or if you preview any kind of media, in this case a 128 megabyte SD card, you will see that there's a the image up here, and then you can get some information from the disk based on the information often in the master boot record and other areas of the disk. So if you've ever wondered how FTK knows that, right, this information over here on the properties panel? Well, it's getting it from the master boot record, which resides at sector 0. There's some good information down here. I've got some red circles down here in the master partition table. You can see from this master boot record on this 128 megabyte SD card that there's only one partition. If you're looking down here, you're beginning to recognize you got 00, the very first byte of the master partition table is for this first entry for the first partition. And as you've noticed, there's only one partition. It's 00. The alternative could be hex 80, which would indicate that it's bootable, but this is obviously not bootable. It's an SD card. Has no operating system on it, so the flag there is 00. And then we've got the starting CHS value 012300, and then we've got 0C. And if you recall, this fifth byte or hex or offset 04, hex 04, 0C is the indicator for which file system? Well, here's a clue up here at the top of the page. FAT32, right? So do you remember what it was for NTFS? It was 07. So if this was NTFS formatted, you'd see a 07 right there. But this partition or this volume is FAT32. So you see the 0C there. And then you've got the next 3 bytes, as you recall from last week. Those are the last sector, CHS, for the partition. And then you've got, excuse me, this information right here. These 4 bytes are the LBA starting address. So the starting sector for this partition starts at hex 61. What is hex 61? Well, that's 6 times 16 plus 1, and I think that's 97 if I'm remembering correctly. And then you've got your the last 4 bytes of the partition entry, which tells you the total size of the partition LBA sectors. Okay, so let's take a look at that real quickly here. We are now looking at our FTK imager with the 128 megabytes. It says 122, but there's a reason for that, because it's got some space that isn't used for data, right? It's got some of that reserve space for the file system and other probably HDA or other protected areas, HPA host protected areas, or things that we can't access. All right, so if I've got this image highlighted, or the actual physical drive up top, we get all of the sectors on the disk from sector 0 all the way down to the last sector on the disk. In this case, it tells us that there's a sector count of 250,880. There's 512 bytes in each sector, and and then it gives us some CHS information there if we wanted to convert it back to CHS. And so we're looking at this information, and again, here's the master partition table. We just looked at it. We just looked at the first entry of the master partition table. I'm sorry, I didn't go far enough. There's the master partition table, and we just looked at this entry, okay? And we found out that the starting sector for the partition is 00000061. And if we use our hex value interpreter over here, it tells us that the value is 97. Indeed, it is, though. It starts on physical sector 97 is where this partition actually starts, which means there's 96 partitions before it which are not used for data and not really used for the operating system per se, or the file system. But here's the first, the first 97 sectors. And we could scroll down and look at all of them, and it looks like they're all Fs. It's been wiped with hex FF values, and so we could just keep going down. Right now we're at sector 56. Boring. Who cares? Okay. So back up to the top, and we'll start to look at some of these other things going on here. All right. So there's your master boot record and your master partition table in a FAT formatted volume. All right, so now we need to look at some of these data areas and these data clusters. And we are going to go back and look at the FAT table, and kind of take a look at some of this other stuff here, but I need you to understand in the when a volume is formatted in FAT32, you've got um, a couple of areas that are really significantly important. The FAT table, or the file allocation table itself, which is basically a bitmap. Okay, and I'll show it to you in a second. A bitmap of every sector on the hard drive or every sector on the media, and which files are located there. Okay, so we'll take a look at that. And then you've got your root directory, which is a list of all of the files or directories in the volume, and they're put out there in 32 byte chunks, right? So each directory has 32 bytes, which is essentially just metadata for the file or the directory that's out there. It tells us stuff like when it was created, where it's at, things like that, the name of it. So that's really important. It doesn't tell us exactly what it is. It tells us where the starting sector is, and then we can go to the FAT table, and the FAT table will then tell us which sectors have been allocated to that file. So those two things in conjunction help the operating system know when you click on a file, it goes to the directory and says, oh, you want this file? Oh, the starting sector is here. Let's go to the FAT table and find that starting sector. And then from there, the FAT table tells us which sectors are all part of that file, whether they're contiguous all in a row or whether they're fragmented in different parts of the drive, and we'll figure out how that is. And then you've got all of your sectors out there. Now, in this particular slide, we've just kind of chunked them up into 4-sector clusters, right? Because that's pretty common. If you would have a 4-sector cluster, that means that you'd have, 512 bytes here, 512 bytes here, 500, 500. So you'd have 2048 bytes total per cluster. So each one of these big boxes is a cluster. Each one of the little divisions inside is a sector. So each one of these represents 2048 bytes. Well, I probably should have used a little more forethought and made this a little bit more consistent with the PowerPoint, but in the 128 megabyte drive that I formatted in FAT32, I just said, let's just make it 1 sector per cluster to make it simple, right? So each sector is a cluster on the actual drive that we're going to be looking at. And so instead of a cluster that's 2048, we have a cluster that's 512. Okay, so I hope that's not too confusing to us. Let's take a look. All right, so here's what we expect to see in the volume boot record. Okay, we got some, again, we're going to do a little byte level analysis of the volume boot record. We'll bounce back and forth between the real thing and our reference chart here. Again, the starting sector, okay, for the partition is sector 97. The sector count is 250,000. And then we'll look at some of these indicators up here, some of these bytes. So at this particular offset, it tells us the bytes per sector, and here at 200 hex is 512. Okay, why did I read it backwards? 0200 because it's in little endian format, which means we're going to start at the right and read left. Now again, just for review, we don't start with the nibble. I don't read it as 2000. I read it as 0200. And if that's not as clear as mud, then we'll look at it again over here when we talk about the reserved clusters from the VBR to the FAT. So how many, remember when we said we've got all these reserved clusters between the VBR and the FAT, and here I've just got these 4 reserved sectors here? No, actually the volume boot record here tells us nope. When it formatted it, it put 4,040 sectors between the FAT or the volume boot record and the file allocation table 1. Okay, and how do we know that? Because again, we've got 1130. So that's a little endian. We're going to start reading with this byte 11, starting with the left nibble, going to the right nibble 11, and then going to the next byte to the left, starting with the left nibble and then the right nibble So 1130. And if you put that into your hex calculator, or if you're a math wizard and you can do that in your head, then you would know that the value is in decimal 4040. This little byte in here is just the sectors per cluster. So as I indicated to you, when I formatted this, I just said let's just make one sector per cluster. So my allocation unit is 512. I could have done 2048, which would have put 4 sectors in there. I could have done 4096, right, which would have put 8 sectors per cluster. But I didn't. I just chose 1, and there it's indicated right there. The next thing over is, or down at the last 4 bytes of this 32. The first 32 bytes here is 61000000. Again, not red big endian, red little endian, and so 61 is 97 in decimal, 97. So we know that there's 97 hidden partitions, right? Or that it starts on 97. Actually, it's 0 through 96, so there are 97 of them. This starts on 97. This value down here is the size allocated to the FAT table currently. Okay, so there are, if you read this backwards, 768 in hex is 1,896 in decimal. You don't have to take my word for it. You can get your calculator out and check it. And then the starting cluster for the root directory. And this is a little confusing. It took me a while to wrap my head around this, but this is cluster number 2, and it's not cluster number 2. In this case, it would also be sector number 2 because I only have 1 sector per cluster. But this is not cluster number 2 physical, right? It's not the physical second sector on the hard drive. Remember, all that stuff is hidden. It's in the first, 96 clusters were not being used by the file system. But this 02, this cluster is the second cluster, logical cluster in the data area. So again, we're going to go back here, starting with the data area. The root directory occupies cluster number 2, and so if we had this first sector here is cluster 0, and then the next sector is cluster 1. Those are occupied by root directory metadata. And then the third cluster down, which is cluster number 2, would be where the root directory actually starts. Okay, so it's telling us that the root directory starts in cluster number 2, and that'll be significant in a minute. And then down here it tells us we also can see that it identifies the file system as FAT32. So there's some good information. Let's take a look at it and take a look at some of these things over here in the volume boot record. So we're going to go here, take a look at our volume. Here's our volume boot record. If I click on the partition, we would expect to see the volume boot record at the beginning of the partition, and there's all that metadata that we were talking about here. Okay, 512 bytes per sector. That's useful. 1 sector per cluster. That's useful. There's our hex 3011, which tells us the number of sectors between the volume boot record and the file allocation table, and we're going to use all this in a second. And then we talked about this. Those are the reserved sectors at the beginning of the drive, right, before we get to the good stuff. And of course, then we've got excuse me, these bytes here tell us that it is a FAT32 file system. Down here, we might expect to see, if this were a master boot record, we would expect to see a master partition table here. But this is a volume boot record. It's not the master boot record, and so we do not see a master partition table here. In fact, we see right here a message that says disk error. Press any key to start. Well, basically, if you tried to boot from this, it would be like, nope, can't do that. This is not a bootable partition. This is a volume that's just used for data, and so that's why it gives us that error right there. And then there's the footer for the volume boot record. All right, really exciting stuff, I know. All right, let's go back to our PowerPoint and take a look at what we got here for you. All right, So we just took all that metadata information and we kind of added it up. We say, okay, we've got 97 sectors reserved at the front, which includes the master boot record, the master partition table, and a bunch of reserved sectors. There's 97 of them total, so from 0 to 96. And then our actual FAT system starts on um, sector 97. Um, and it occupies from the beginning of the the volume boot record to the first file allocation table, 4,400 sectors, which we got from the volume boot record. Remember, it told us that. So in the volume boot record, it told us that there's 4,400 sectors before the first FAT table. That's good to know. It also told us that there were 1,896 sectors in each FAT table. So if we now know, we can figure out the physical location where the data actually starts on the drive, right? The data actually starts down here on sector 8289 of the physical drive. We know that because we can add 97 to 4400 to 1896 to 1896, and that gets us to 8289. Actually, it adds up to 8290, but we have to take one back for logical block addressing, right? Because we start at 0. All right, so let's do that really quickly, just because I know you're so excited to see that. So we're up here at the physical level. We're on the physical hard drive, and we want to, I mean, we could just click on the root and click on it, and it tells us, that, it's right there, 8289. It tells us the starting sector for the root directory. So FTK, thank you for automating that for us. We don't have to do all this math every time. But if we wanted to start up here at the physical drive level and go down to sector or cluster 8289, right, bam, and now we're down there, and look at that. There's the root directory starting right there where we would expect it to on 8289. All right, so this is what your root directory actually looks like. Okay, these are all of the entries for your directories and your files that are stored on this particular piece of media. Now, if I were to click here on the partition itself, on the formatted part of the partition, it takes us to the data area. The first entry is the root directory, and FTK Imager does a beautiful job of kind of aligning it up in this GUI, format, so we can see files and folders and everything like that. But in reality, the data is not laid out exactly like this on the disk. The data is laid out first and foremost in this root directory in these 32 byte chunks. So when we look at it and we see a folder that says root, well, that's very nice for us as humans, but that's not how the computer sees it. The computer sees it actually as a series of 32 byte chunks, which tell us a lot of information about all the stuff that's stored in there. Okay, so what kind of information is stored in the root directory? Well, glad you asked. Let's take a look at that. Root directory entries, the first 11 bytes are for the short file name and the file extension. Okay, so in this case, we're looking at on this particular case, I think what we're looking at here is thankfully it's in ASCII, and a file called sdcard.png, and so that's what we have here, SD-CARD space. It's filled with a space, and it pads it with a space. There's not actually a space in the title, but it pads it, and then the next three bytes are the file extension, so PNG, right? So those are just ASCII codes, right? When remember week 1 we were looking at ASCII codes and hexadecimal. That's all that is, and it's readable over here in the right-hand text column, all right? And then there's some kind of other metadata associated with the file, which we're not going to get into too deeply here, but you need to know that the file table, the directory entry in the root directory, I said file table, I didn't mean file table, includes metadata like the creation time and the creation date, and those are actually typically packed bytes, which means you have to kind of put them all out there in binary and then share them a little bit, but you could use something like Decode, for example, which is an open source or freeware utility from Digital Detective, and you put in you just highlight, right, 4C89708F, and right click and say um, copy hex value, and then you just paste it in here. Paste it in there. Whoops. Um, and then you have to pick the right format. In this case, it's MS-DOS 32-bit hex, and make sure if you want the correct time zone to display that you choose if you're in Arizona, -7 GMT or -7 UTC, and it'll actually decode it for you. It does all that for you. We could go through exactly how to do that manually, but it's not the most important thing to learn in this class, so just know that it can be done, that there is a way to manually decode that as a matter of bytes. But you've got utilities like decode which can do it for you. All right. And so we're looking here again still at SD card PNG. You can see it in the file view or the file list pane of FTK Imager. There's the file. It's not deleted. It looks just how you'd expect it to. And down here, it tells us the starting cluster, right? 6D01, or actually, because it's little endian, 016D, and that is the starting cluster relative to the beginning of the root directory. So if the root directory starts at 0 and the root directory itself is cluster 2, then you're going to go to cluster 365. Hex 016D is 365. And if we wanted to find out where that was actually physically on the drive, if we wanted to start from the physical level, then we'd have to add all those other clusters, 8290 or 8289, and then we could go out physically to the drive on the physical level and see where we're at. We'd have to go to starting cluster or sector 8653. Why? Because we're taking this 365, right, which is the logical location, and we're adding that to those 8290 bytes or 8290 sectors that are in the system prior to the root directory. So we've got these 8290 or 8289, and then we're going to add the 365, and we have to count for the fact that it starts at 2, and so it takes us out there to 8653. So let's go ahead and take a look at that in FTK Imager. So back here at the physical level, if I right click and say go to cluster, I want to go to 8263, I believe it was. Let's see. Nope, I miscalculated. I didn't remember it correctly. Oh, way off. 8653. 8653. Doofus. Okay, so we'll go back. We're just up here at the physical level. This is sector 0 of the physical hard drive. We want to go to 8653, if I remembered it correctly. 8653, and hit OK. And there it is. Oh, and look at that. That's beautiful. We know it's a PNG file. We can tell by this file signature right here that is a PNG, and it looks, yep, that's probably our card that we were looking at, our file. So this is just an SD card PNG, and it's the one that you saw in the PowerPoint, right? So there it is on our hard drive, on our SD, a picture of an SD card on an SD card. It's kind of Inception-esque. I didn't want to confuse you too much, but I'm just making sure you're staying with me on this. Okay, so that's what it looks like in human readable form. In hex value, this is what a PNG looks like. That's what the computer sees, and that's where it is out there on disk. Now, starting at sector 8652, which is actually the 8653rd sector, because we start at sector 0 always. Okay, all right, so that's now you can see the actual physical data, okay, the physical data, and we also looked at the directory entry, right? So if we go here to the directory entry, where is the SD card PNG? It's right here, those 36 bytes. So we've got some metadata about where it starts, right there. It starts out there, whoops, let's go to hex value interpreter, at cluster 365, starting from the beginning of the root directory. right? So um, this is just, oh, look at all those files. So if we're at the volume level here, and I go to sector 365, that should take us right to where we need to go. Let's hope I don't embarrass myself here. 365 is out of range. Of course it is. Let's see. Oh, why? Um, got ahead of myself. All right. So now that I've completely lost my train of thought, let's go back to the PowerPoint to get back on track. All right, so we looked at the directory entry, we looked at the starting cluster or the starting sector as recorded in the directory, and we also found it physically on disk. Okay, and that's where I got lost. We are actually trying to go out to sector 365 and see if we could find SD card out there. And for some reason, I did not find it out there. It should have been out there. Let's see. So try again. Cluster 365. See, this goes from cluster 2 to 20. So let's go. Okay. It's not out of range. Stop telling me stupid stuff. Cluster is definitely not out of range. Why is it saying that? 365. Okay, I don't know why it did it the first time. I fat fingered something, but there we go. There we are at 365, and there's our SD card PNG. Okay, so now we've seen a couple different ways to navigate to the data on disk. This is actually data on disk, and we went there physically from the beginning of the hard drive, right? So it's out there in the 8000 cluster, 8600 cluster physically, and that even tells us in FTK. That's what I love about FTK, 8652. But the logical cluster from the beginning of the volume is 365. Okay, so that's really useful information. We now know how to physically find the data based on just the directory entry. But what we really only know is how to find the first sector of that file. Just if we're just looking at the directory entry, right? We're looking at SD card PNG. It doesn't tell us. It tells us how big the file is total, but what if the file was fragmented? That would be a problem. As long as all the files are contiguous, we're golden. We really only need the directory entry and access to the data portion of the disk, right? Because we can go out there and we can find 365, or we can add 365 to the 8290 or whatever it is and come up with the 8600 block range. So we could find the starting sector, but if all of the sectors of this file aren't contiguous, we're in trouble, right? If it's fragmented, we only know how to find the first fragment. Okay, so that's where the file allocation table comes into play, and we'll get to that in just a second. So, all right, sequencing goes like this. I lay a file to disk. I copy it to disk, or I save it to disk, and let's say I save a file called USB drive.png to disk, and it takes up the first 359 sectors of the data section, right? So I've got a file here that's starting in sector or cluster 6 or sector 6, and when you look at a file allocation table, you have to kind of imagine a big shelf on a huge warehouse wall, and there's boxes on the shelf. They're all the exact same size. Each box on the shelf is 512 bytes, right? And so it's a big bunch of boxes up there on the shelves, and they're all uniform and neat and orderly, and they're all numbered sequentially perfectly. So I take the first 364, well, not really, 359 boxes on the warehouse shelf, and I start putting data in each one for that USB. Um, and I'll show you what I mean. Right, we've got this USB drive PNG. Let's look at it. It's a beautiful picture of a USB drive, right? And it's got a lot of bytes, right? It's 183,880 bytes. Well, if I divide that by 512, that's a lot of clusters, right? That's, in fact, it's 359 clusters. So that's how many boxes I need on my warehouse to store this file. So I break up the file into 512 chunks and put them in each box, and it starts at starts at cluster 6, and it goes all the way to cluster 364 on this shelf. This is a big warehouse. I've got a lot of boxes. All right. Now, the file allocation table is the warehouse foreman's chart. The warehouse manager's got a clipboard with a chart, and it basically says, okay, I've got a directory here. That's our root directory, and it says that file USB drive.png starts at cluster 6. So he goes to his file allocation table, his spreadsheet, like we're looking at right here in front of us on the screen, and he says, oh, okay, cluster 6 right up here. It looks like USB hard drive is a contiguous file, starts at cluster 6, goes all the way to cluster 364. And in the actual file allocation table, it's not truncated like this. It's a bitmap. It's just rows and rows and rows and rows of sectors. And here's how we know it's contiguous, because cluster 6 has a marker in it that says go to cluster 7. So you go to cluster 7. Cluster 7 has a marker in it that says go to cluster 8. You go to cluster 8. Cluster 8. So imagine, again, we're in the warehouse, and the boxes up on the shelf actually have placards on them, right, that say go to the next chunk of this file is stored in box 8 or cluster 8. And so you go to box 8, and sure enough, it's got part of that PNG file in it, and there's a placard on it that says go to 9. And so you keep doing that until you get to the end of the cluster. And when you get to the end of the file, or not the end of the cluster, the end of the file, there is a placard on the box on the warehouse wall that says hex 0F or FFFFF0F. And that's pretty typical how it's going to say end of file, right? So we know now that USB drive.png ends in cluster 364 because it's got that placard on it that says 0F. Okay, and if you look up here in the gray section of my little chart here, there's some indicators. Your box could say 00 on it. Your warehouse box could say 00. In fact, down the row here, several shelves down, I've got my first box that says 00, and all the rest of them after it say 00. Why? Because there's no data in there. It's empty. That just means it's an empty box. It's unallocated. It's ready to take data. Okay. FF or 0F would indicate end of file. A number there indicates the next sequential sector or the next sequential box on the shelf where data from that file is stored. And then it might have an F7 or some other indicator there that says this is a bad cluster. Bad cluster. Don't use this. This box has a hole in it. We can't use this. Don't use this warehouse box. It needs to be fixed or replaced. We're just going to skip it and don't put anything in here. Okay. So that's if you visualize it like an actual warehouse. That's what your hard drive is. It's a warehouse for data. And so you've got all these placards on the boxes that indicate where the data is. And that's what the master file table tells us, right? The file allocation table, the guy with the clipboard says, yep, okay, I've got, I just put USB drive.png in there. Now I need to put SD card.png in the warehouse. And so I go to the next place on my clipboard, which is cluster 365, and I start bringing in the forklifts and dumping in data from this file, and 512 bytes go into cluster 365. And so then I slap a sticker on the box or a placard on the box that says go to 366, and I put the next 512 bytes in 366. And I keep doing that down the line, down the line, down the line for 202 sectors or 202 boxes on the shelf. I've got 512 bytes in each one. I get to the last one, cluster 566. It doesn't fill it up all the way. There's a little bit of space left in 566, but I can't put anything else in there, right? It's just you can only put one file type or one file in a box, right? So there's some leftover space in the end of box 566. There's a little bit of space in there. I could put some more stuff in there, but I'm not going to, right? Because my protocol says don't put any more stuff in there. We're just going to leave it blank. What's that called? Do you remember from the beginning of week 1? That's called file slack. Actually, that might have been from CFR 101. But anyway, that's what we're talking about right there is how to allocate the files by the file allocation table. Okay, now so let's take a look at that. Let's go look at what an actual file allocation table looks like. We've got this nice pretty picture here. We've talked about it being in the warehouse shelves. Let's look at the file allocation table. Now we can, FTK Imager makes it really easy. We can just click on file allocation table. We could go up here to physical drive and using our little byte map that we did in the beginning, right? We could say, okay, my first file allocation table starts in 4,497 sectors, so I could go there from the beginning of the disk and it would be there physically, but FTK Imager makes it a lot easier than that, right? FTK Imager makes it super easy. So we're going to just go over here to our first file allocation table and we're going to take a look at it and see what it looks like. All right, so file allocation table 1. Remember, file allocation table 2 is just a mirror image of file allocation table 1. And so here we go. The first, sector 0 and sector 1 contain metadata, presumably telling us that this is the beginning of the root directory. This is the beginning of the data area of the hard drive. This is the beginning of the partition right here. Here it is. Here's our marker for partition 128 megabyte SD. That's our volume label. Okay, so now sector 0 is represented by the first 4 bytes. Sector 1, and this is logical sector, this is the sectors of the data area, is represented by the next 4 bytes. Okay, sector 2 is represented by the next 4 bytes. And with the, we know that this represents this file here. It doesn't tell us what file it is. We don't have any data here about what file this is. But we know that this sector represents the root directory, right? We know this sector represents the root directory because when we're in the root directory, jumping back to the root directory tells us, right? Actually, I just made that up. Not the root directory. The volume boot record told us that the root directory starts in sector 2. Okay, so we know, or cluster 2, we know looking at this that sector 2 is the root directory, and we know that it. Now here there's something a little funny going on because the root directory is expandable, right? It's not a set. It's not a set size. It's got to be expandable. So it's actually pointing us out to somewhere else on disk, and then pointing us back. And now, right now, the root directory is two sectors long. How do we know that? Well, if we go to the root directory, we can look at it, right? So here's sector 1 of the root directory. We don't have much stuff in here. This is the root directory. It's pretty empty. This is, even though it's only 120 megabytes, there's hardly anything in here. We just got these few files here and a couple of directories and some deleted stuff, right? So if we look at this, here's the first sector of the root directory, and we scroll down, and there's the end right there. There's the second sector of the root directory. So we know it only actually occupies 2 sectors of disk space at this time, and the file allocation table reflects that nicely. So if we look at our file allocation table, we can see sector 2 is occupied by the root directory, and then we have an end of file marker. This is the placard I was talking about that's on the this is a warehouse box. this is a warehouse box, this is a warehouse box, and this is a warehouse box. Every 4 bytes in the table represents one of those boxes that I was showing you back here in this chart. Okay, each one of these boxes is represented by 4 bytes. Well, that's what it looks like in a hex editor or hex viewer, right? So this box right here is the last box occupied by the root directory. Now we've got another file here. We don't know what file it is, just looking at the file allocation table, not sure. It's probably one of these directories in the root directory, right? Because one of the first things I did when I created this is I created this new folder and called it empty directory, and then I created another folder and called it document directory. And so if I had to guess, I would say that these first couple of entries in the file allocation table after the root directory's 2 sectors, these are probably the directories that I created. Okay, and then we're here at 0, 1, 2, 3, 4, 5, 6. So the 6th box, 7th box actually, but it's actually the 7th box, but it's the 6th cluster because we start at cluster 0, right, logically. And it has a placard on it. Can you see the placard? Right? The placard on that box is 07. And that basically tells us, hey, it's time to go. The rest of this file is in cluster 07. So we go to 07. There's cluster 7. And it tells us, oh, there's a placard on there. Go to 08. And then so we go to 8, cluster 8, the 8th box, right? Oh, it says go to 09. And this happens infinitum. Not quite infinitum. It just feels that way. So there we are. This one says go to 10. You said it doesn't say go to 10. It says go to 0A. And you're correct because hex 0A is the same thing as decimal 10, which you knew that. All right, so there you go. And then this one says go to 11, and this one says go to 12, and it just, there's no break. It just, and this is when you look at, because it's sequential, right? You look at the ASCII over here in the right-hand column, and you see these sequential numbers and letters as though you're looking at an ASCII chart. In fact, that's what you're looking at, because FTK Imager doesn't know what to do with these numbers over here. So it just puts in the ASCII number for it, right, from the ASCII chart. So it's just telling us, yeah, hex 21 is an exclamation point. Well, we don't really care what the ASCII value of this is, because it's not really telling us anything about that. It's just telling us to go to cluster 21. So we go to cluster 21. It says go to 22. So if you see something like this down the right-hand column, you can be assured that you are looking at some kind of a bitmap system, some kind of, and probably a file allocation table. So you see these chunks of ASCII code over here that are sequential. They're perfectly sequential. And as you get up in the numbers, they get weirder, right? They become like these foreign diphthongs and things like that. You know, I don't know, webdings, whatever they are, but they're still sequential ASCII characters. This is indicative of a file allocation table. All right, and it just keeps going. And you keep going down there. I would assume, well, let's not assume. Let's go back to our root directory. And we're going to look and see our 6th entry. So we got, here's an entry, 3, 4, 5, 6, 7. There's a long, so that's a long file name. And then here we go, USB drive PNG. Okay, there's an entry that roughly correlates to what we were talking about, the data that we were looking at. And here's our, tells us right there, our starting cluster is 6. Okay. That's very interesting. Okay, so the starting cluster for USB drive is 6, and that's good to know because now we can go to our file allocation table, and we go to our 6th entry, and there it starts. And how big was that file? Oh, we should have looked at that. USB drive, right? Well, I'm just looking at the USB drive right now. We know that it takes up on disk 183,808 bytes. And if we divide, this is the SD card PNG, but if we divide that total number of bytes by 512, we get 359 sectors, right? So we know it's going to take up 359 sectors. That's how we know that. Anyway, we got to get through this because you guys are going to be falling asleep. This is super exciting stuff, I know. So that's what we're talking about right there. SD card PNG, same thing. Starting clusters 365, and that it is in size 103,000 bytes. So we divide that by 512, and that gives us the total number of bytes that are going to be taken up. Total number of boxes that are not bytes, total number of boxes, total number of sectors, clusters taken up by the file, and that is reflected in the file allocation table. Okay, so it's just going to keep going for 5, what did I say? I've already forgotten how many it was going to be. But if we scroll down, we're going to scroll down a little bit, and we're going to see a break here pretty soon, and we're going to see this. That's the box I was looking for. Do you see that? That box over there tells us that that is an end of file marker for that group of boxes, right? So if we're looking at our pretty picture again, there it is, cluster 364, FFFFFFOF, okay? And then we're going to start the next file, sdcard.png, okay? And so sdcard.png starts right there. And this is really great, right? Because this marker right there is pointing to the next box on the shelf or the next cluster. And if we look at the value system here, it says it's pointing to 366. We know that this is 365. What was the starting sector for SD card PNG? 365. Okay, so this file allocation table is actually showing us right here. It's a bitmap. It's a chart. This is 365. It points to 366. We go to 366. It points to 367. We go to 367. It points to 368. And that just keeps going for 202 sectors. All these blue boxes. 4 bytes every box. Okay? And then it's going to end on cluster 566. Well, let's see if that's true. Let's double check. We're going to scroll down until we get to the end of this bitmap. And there it is. Let's see. Let's look. There's our end of file. This said it's going to end on which cluster? 566. There it is, 566, end of file. Okay, so that's a file allocation table, and that's how it allocates sectors to a file. Now, what if we wanted to delete a file? And now we're going to go out on a limb here. We're going to do this live and see what happens. I'm going to go and I'm going to delete this USB drive PNG, right, which is the pink area up here. So clusters 6 through 364, I'm going to delete them. And what I would expect to happen is for the file allocation table to go in and zero these out to make this not point to 8, not point to 7, not point to 9, not, what did I say that backwards, but you know what I mean. It's just going to zero out the table, right? That's what I would expect to see. If I go in and I delete, I keep clicking on the wrong thing. If I delete this file starting right here at cluster 6, all the way down through 365 or 364, what was it? Anyway, if I delete all of this, I would expect for these numbers, these placards to go away and everything just to be 0. Okay, I would also expect in the volume directory, the root directory, I would expect this USB drive .png, I would expect this right here to change from 55 hex 55 to hex E5, right? And that's just an indicator in the FAT file system that this file has been deleted. Now, what doesn't happen is it doesn't go out and zero out the data on the disk. So the actual data, the actual clusters on disk that contain the data for this PNG aren't touched, right? All it does is it puts a little marker here on the first, it flags this first byte of the directory and says, no, that's an E5 now, which means we can overwrite this directory next time we want to. And it's going to go into the file allocation, the file allocation table, and it's going to zero out all of these entries, those 365 entries or whatever they are, 359 entries. It's going to zero them out and just tell the file allocation table, okay, we can put new data in here. Okay, so let's see if that happens. Let's do a little experiment. I don't know what's going to happen. I honestly don't. Probably going to look stupid. Probably not going to work. It's going to be like, you're an idiot. Okay, so I'm going to go out here. I'm going to go to this PC. I'm going to go to my 128 megabyte SD card. There's SD card. I want to delete USB drive.png. So let's just delete it. You sure you want to permanently delete this file? Sure, why not? It's gone. All right, let's go back into FTK Imager. Let's remove this. We'll add it back in now. Physical drive. And we want this generic 128 megabyte. All right, let's see what happened. Let's go check. First of all, let's just look in the root directory. Oh, USB drive has a red X to it. That means it's been deleted. Okay, let's look at the root directory itself for USB drive down here. Here's our 32 byte entry. Oh no, that's SD card. Sorry, USB drive, where are you? USB drive PNG. And sure enough, it changed to hex E5. All the metadata is still there except for the first letter of USB drive.png. It's now this funny little A with a diphthong symbol over the top of it, but that's the ASCII value for hex E5 for this system. Okay, so there you go. Our root directory has been updated since that's been deleted. Let's go look at the file allocation table and see if, as expected, holy crap, starting with 6, it's been zeroed out. Look at that. There are no more, all the way down till we get to the next file, right, which is actually this one. And that's our SD card PNG. It starts right there on well, that's looking at the physical cluster. But we know that this is actually cluster 365, right? Or 360, yeah, cluster 365 from the beginning of the data area of the disk. Okay, and so there's the first box of the next cluster. So what happens with these zeros in the file allocation table? That just tells me that if I want to write another file here, I can drop another file here and it will probably use this space. Okay, what if the file is too big for this space? Well, it depends on the operating system, how it utilizes the file system, but in legacy systems, what it would typically do is it would, let's say I want to write a okay, so we deleted our file, gone. It zeroed out the file allocation table, so there's no more data in those 359 sectors. It's just zeros, so there's no pointers. What else did it do? It changed this 55, not 55, hex 55, changed hex 55 to E5 as expected. And so what happens if we want to drop another file in there? What happens if I want to save this PowerPoint, for example, to my SD card? Well, in theory, what it should do, and what it's done in legacy systems, is it should overwrite these first 359 sectors, And then it should go to the next available sector, which is down here, cluster 567, and continue writing the rest of those 2,624 sectors required for this drive. How do I know there's 2,026 sectors required for this file? Because I know that the file size is approximately 1,343,488 bytes. If I divide that by 512, that tells me the total number of sectors required, which is 2624. So I would expect it to take up 359 sectors here, which have been zeroed out. That's effectively going to overwrite the data on the disk out there. Okay, it's going to fill it all up with PowerPoint, and then it's going to point this cluster 364 is going to point to cluster 567, and then it should continue writing out the rest of these 2,624 bytes. Okay, so that's what I would expect to see, is something like this all the way through cluster 2591. All right, so at that point, right now this data is still out on disk from the old file, from USB drive .png. It's still out there on disk. We can confirm that if you want. You do? Okay, fine. So what we want to do is go out there on disk. And we said go to, what was it? It was cluster 6. And there we are. And as you can see, our PNG file is still there. So up to what does this mean for us forensically? It means for us up to this point, this data is still recoverable. Even though it's been deleted from the drive, this graphic image file, this PNG, picture of a USB drive, is still recoverable. We can go in here and recover it. We can grab these bytes and we can recover them and export them out, and now we've got evidence. Let's say that was an important evidentiary file. We could still get it, but if we, what happened? Stupid. Sorry. If we overwrite it with this PowerPoint, those first 359 sectors are going to be, not only is the file allocation table going to be filled, but it's actually going to write data out there on the hard drive. Okay, so that's really critical to understand, that if you overwrite data, it's gone. It's gone. Okay, so let's see what happens. Let's do this. Let's do a little experiment. Okay. We want to actually go out here. We want to, you know what I'm going to do? I'm just going to, you won't be able to see it. I'm just going to go File. Maybe I'll move it over here so you can see. Got my PowerPoint, right? FAT32 file system, File, Save As, and then I'm going to put it out here on to 128 megabyte hard drive. Just save it out there. Save. Bam. Now, the big question. The big question. Did it, in fact, overwrite these clusters and then finish writing the file out here, or did it start out here at 567? I honestly don't know, right? It may be, with Windows 10, maybe Windows 10 treats FAT32 differently than older versions of Windows. So, who knows? Let's see. Let's go look at FTK Imager again. We're going to remove it and re-import it. And 128 megabyte drive. Okay. Well, let's just take a look graphically. Let's look at the GUI here. Let's see what's in. All right. FAT32 file system is now on there. Okay. It says its starting cluster is 571. Well, that's a really good sign for us. That means it did not overwrite that file that was originally at cluster 6. Okay, so let's take a look. Let's look at the actual root directory. Let's scroll down here. FAT32 PowerPoint. There it is. And if you remember correctly, right? We want to see what the starting cluster is for the entry in here. Okay, so it's these last 6 bytes of the entry, right? So the first 2 of the last 6, does that make sense? First 2 of the last 6, so here's the last 6, 3, 4, 5, 6, so it's these 2 bytes. And if we look at the hex value interpreter, it tells us 571. So it did not overwrite that first file. So even though that first file, let's take a look at the file allocation table. That first file's table, FAT table entry has been deleted. It's still zeroed out. Windows 10 did not rewrite the larger file to this place. It did not fragment it. It went ahead and put it out here at the end. And what we want to do is kind of look at 571 out here. Where are we? Is it 571? Yeah. 566. Here we got, and there's our end of file right there. Okay. A bunch of end of file things going on here, and 572. Okay, so here's our end of file marker for our old data, and now we're going to start with the PowerPoint. PowerPoint starts right here. That's the first file allocation placard for the PowerPoint, and then it goes a long ways down. It keeps going, keeps going, keeps going. It's a big file. There it is. There's the end of it. And again, this isn't the data from the file. These are just the placards on the boxes in the warehouse, right? These are just the placards. This isn't the data inside the boxes. These are the placards on the box, all right? So, and then there's our end of file marker at the end of the PowerPoint. I hope this was helpful to you to kind of get an idea of how the FAT file system works, okay? In review, we looked at the file allocation tables and how the file allocation table in the FAT32 system is a 4-byte marker system. Those are essentially placards on the box in the warehouse, okay, that point to the next box. We also looked at what happens if you delete a file. 2 really important things happen. Number 1, it zeroes out the entry in the file allocation table. It puts all those placards on the boxes to 0. Now the data is still in the boxes unless I come along and dump a bigger file in there or another file in there. Depending on the operating system, it could dump data right in there and remove the old data and dump new data in. In this case, it didn't. Right? So we have our PNG file. It's gone, at least to the operating system. Operating system can't see it, but with tools like NCase or FTK or Autopsy, we can go in and recover that data if it hasn't been overwritten. All right, it changed the directory. If you remember, in the directory listing, the root directory, there's a 32-byte entry for each directory or file. In this case, the USB drive.png, it changed the first byte from 55 to E5. We witnessed that. And then we did a little experiment. We dropped in a FAT32 file system PowerPoint, a much bigger file, 2,624 sectors, onto the drive to see if it would fill up these clusters and then fragment the file. It didn't. It did not do what was anticipated. It started out here at cluster 567 and went all the way for 2,624 sectors out. So it did not do what was anticipated, which many Windows operating systems will. Many Linux operating systems will. So if you write a bigger file, it will overwrite data and the file table to reflect that. In this case, we as the examiners got lucky. The bad guy did not, his evil data did not get overwritten, which means we would be able to recover it with a Windows 10 using a FAT32 file system. Now, there may be other parameters within the Windows 10 system that said if the file's this size versus this size, then it will go back and overwrite it. I'm not sure what that is. We'd have to do some experimentation. So anyway, hope that was helpful to you. Hope you stayed awake. I know this was a rough one. This one's long. We're over an hour. Good job. We'll talk to you later.